Hello and welcome to lecture 14, differentiation of logs and log differentiation. Okay, so what we're going to do is we're going to learn to differentiate logs using the tool of implicit differentiation that we learned from the last lecture. And we're going to use this to learn a method of differentiation called log differentiation, which is incredibly efficient to differentiate quite difficult, quite complicated expressions. So let's start where we were last time. So we know the exponential function, to the x. We understand well its graph. And from this graph and some elementary considerations, we got a pretty good idea what the graph of log looks like. Something like this, right? Where this is 1. So we would like to get a better understanding of this using implicit differentiation. So this is what we're going to do. And let's do it in greater generality, all in one go, because this guy is just a special case of b to the x, right? And b to the x has a graph very similar to this. And so it satisfies the horizontal line test. For every horizontal line, it only intersects once. And its inverse is given by this function log to the base b of x. This is all this is. It's just the inverse of b to the x. Okay? So we are going to get an understanding of these guys using implicit differentiation, and this is how we do it. We say, okay, let y of x be log to the base b of x. Yeah. Then, what's the defining property? This is the inverse of b to the x, so b of y of x is equal to x itself. Right? And this is an implicitly defined equation, right? So we can differentiate through this. So take derivative. Oops. And what do we get? Well, we have to remember how to differentiate b to the x, right? Because the outer function is b to the x, the inner function is y of x. So recall, b to the x, we write this as e natural log of b to the x, right? Which is e this. And if we differentiate this, what happens? Well, we have the chain rule. The outer function is e to the x. The inner function is x log b, right? d by dx, b to the x. What happens? We're going to have log b, e to the x, this thing, which is log b, b to the x. We did this before. If you are not comfortable with this, work it out. Don't remember it, working it out. And this trick of having b to the x and writing it as e log b is a trick we'll use over and over again. Typically when we have something to some other thing which is a function of x, we don't understand it in terms of itself this way. We're going to first write the thing itself as e log, because then we're differentiating log of something. Sorry, then we're differentiating e of something, which is what we want to do. So we will use this trick many, many times, so it's worth getting used to this. This is the only thing you have to remember. Just write b to the x as e log b, and then it's easy to figure out the derivative of this guy, and so we have it. Okay, so we need that because we need to try and differentiate this expression here, right? So if we take the derivative, d by dx of b of y of x, the outer function is b to the x, the guy we just discussed, the inner function is y of x. So by the chain rule, it's the outer function applied to the inner function, so it's going to be log of b, b of y of x, and differentiate the inner function, we just have y prime of x. And if we differentiate on the right-hand side of this, differentiating x with respect to x, we just get 1. So this implies that y prime is equal to all of this thing divided through. But b of y to the x is just x, right? So when you divide this stuff through, what we have is 1 over natural log of this divided by x. Okay? So many of you presumably already know that the derivative of log is 1 over x. This is why. Okay? And having done this calculation, let's compare it to the pictures. So what do we see for the graph of log? We see that for x, which is very, very small, we indeed have a very steep positive derivative, right? And the derivative flattens out and flattens out and flattens out. It never gets completely flat, but it gets smaller and smaller because log continues to increase, right? Log continues to increase. So this guy is indeed looking very much like the function whose derivative is 1 over x. So math conforms with our picture, which is what we always want to do. We first want to have some idea what we expect to happen. We draw a picture, use the language of math, do this calculation, get some answer, then we compare back and see if the thing that we've calculated makes sense with what we understand. And that's exactly what happens. Cool. All right, so let's write that just as a separate line. So d by dx of log to the base b of x is 1 over natural log of b to the x, and that's our first thing that we have to learn. So in particular, derivative of natural log is 1 over x. Okay, this formula shouldn't be a surprise because we know that b to the x is quantitatively quite similar to e to the x, so the inverse will be quite similar to log. And b to the x only differs from, well, I should be more careful. The derivative of b to the x is just a constant times b to the x, so they're really quite similar in their derivatives. So we'd expect log to be really similar as well. And the only difference between log to the base b is that we have a constant in front of the x when we go 1 over the x. Yeah? And when we stick in b is equal to e, then log of e is 1, so we get back the formula just for log, which is what has to happen if this was correct. So this formula should seem quite natural, but again, don't try and memorize it. Just do this a couple times to make sure you can work it out, and then you'll have it. All right, so these are our guys, and now we can do some examples calculating with derivatives of log. So this is the first example. Let's differentiate log of x squared plus 1. Okay, solution. It's going to be the chain rule. The outer function is log. The inner function is x squared plus 1. So if we differentiate the outer function, we get 1 over x, but we apply the inner function to it, so we're going to have this. And then we differentiate the inner function, and we're going to have 2x. So this is 2x over x squared plus 1. And that's it. Cool. Actually, since we're talking about this, more generally, change color. If we differentiate log of f, exactly the same reasoning, differentiate the outer function, apply it to the inner function, and then differentiate the inner function, we have this. And this is well worth getting familiar with because we're going to see this later and it comes up a lot. So in this case, f is just x squared plus 1. We differentiate it, we get 2x, so it's f prime over f. Cool. So, first example is done. Let's do another. Let's derivative of square root of natural log of x. Okay. So the outer function is the square root. right? And the inner function is log, so differentiate the outer function, apply it to the inner function, 1 over 2, natural log of x to minus 1 over 2. And differentiate the inner function, we have 1 over x. So we have 1 over 2 square root of log of x times x. That's it. Let's do another. A little bit trickier. Let's do this guy. Let's do log to the base 10 of 2 plus sine of x. The only reason this is trickier is that we're differentiating log to the base 10, but we've learned how to do it. We have the formula over there, right? So the outer function is log to the base 10. The derivative is 1 over natural log of 10 times x. We apply that to the inner function. So we're going to have 1 over natural log of 10. And then the inner function, 2 plus sine of x. And then we differentiate the inner function. And we're just going to get cosine of x, so let's just put it right here. Cool. And that's it. All right. Let's do another. This is example 5. Let's take the derivative of natural log of x plus 1 over square root of x minus 2. Okay, so it's looking a bit more complicated, but let's just do it. So the outer function is natural log. We differentiate the outer function, apply it to the inner function. So it's going to be 1 over x, where x is going to be the stuff inside the bracket, right? So 1 over the stuff inside the bracket is like flipping the numerator to the denominator and vice versa. So we're going to have square root of x plus 2 over x plus 1. And then now we want to differentiate what's inside. So we're going to break it up into a smaller step. So let's just write this before we do anything else. Like this. Yeah? Cool. Now we can differentiate. So when we have something which is a bit harder, we simply break things up into the smaller steps that we understand. And when you're learning something for the first time, if you're having difficulty with it, just do that. Just break it up into the small steps, and then each little step is something you're confident about, and then take it all the way to the end. And if something goes wrong, you can identify where things went wrong. All right, so let's do this guy. Square plus 2 over, is it plus 2? It's minus 2. Typo already. This is minus, and this is minus. Just as I was talking about identifying where things go wrong, I do something wrong. Okay, but now we're set. So this thing, and then quotient rule on this guy. So everything over the bottom guy squared. So we have x minus 2. Differentiate the top, leave the bottom alone. Minus, leave the top alone. Differentiate the bottom. Okay, so looks kind of a mess, but there's an obvious thing we can do to make this better, and that's to multiply through by the square root of x minus 2, because that will make this thing just be x minus 2. We'll kill the square root, and that'll kill this term. So if we do that, then we're just going to have x minus 2 minus 1 over 2 x plus 1. And then we're going to have x plus 1, x minus 2. Looks better. I don't like this half here, so I'm going to multiply both the top and the bottom by 2. And if I do that, I'm going to have 2x minus 4 minus x plus 1 over 2 of x plus 1, x minus 2. All right, one of the x's will cancel. We're going to have a minus 4 minus 1, which is minus 5. And we're going to have x minus 5 over x plus 1 there we go. And that's the answer. So it's just doing what we know bit by bit. However, if we look at this a little bit more carefully, we notice some cool stuff. So log has this basic property of, let me put it over here, that it turns products into sums. Yeah. And as a consequence, it also turns division into subtraction. So log of a over b is log of a minus log of b. Okay, and some of you might be a bit rusty on this. It's not a mysterious thing. It's just from the fact that log is the inverse of e. So actually, let's before we do anything else, well, actually, since we still have this right here, let's use those properties to do this in a different way. And then on the next board, I'm going to give you a little recap why this is true. Okay, so take it for the time being that this is true. As a consequence of this, if we actually have powers, so this also implies that if we do log of a to the p, then that is p times log of a, just from applying this over and over again, right? And it's actually true for any power. So let's use this to do this in a different way, because here we have log of this thing divided by this thing. So let's call this thing star. So star is the same as the derivative of log of x plus 1 minus log of the square root of x minus 2, which is the derivative of, well, we can figure out the derivative of that part straight away. Right? We know the derivative of log of x plus 1 is just 1 over x plus 1. So let's just write that down instantly. And this is 1 over x plus 1, and this is minus 1 over 2, because we are using the fact that log of x minus 2 to the power half is a half log of x minus 2, and then when we differentiate log of x minus 2, we have 1 over x minus 2, which looks like it's a different answer, but if we make a common denominator, so if we have 2 of x minus 2 on the top minus x plus 1, and the common denominator of 2, x minus 2, x plus 1, we have exactly the thing that we did before. We get exactly the same answer. We're going to have x minus 5 over 2, x minus 2, x plus 1. Right? Same answer as over here, but much faster. Okay, cool. So how did this work? This worked because logs turn products into sums and quotients into subtraction. And it's way easier to differentiate the sum of two functions, because the derivative of f plus g is f prime plus g prime, and the derivative of f minus g is f prime minus g prime. These things are way easier to differentiate than f over g or f times g. So it's very good to use that when we have log of something. And that gives us a hint of what we'll shortly see, which is log differentiation. Okay, first let me clean the board, and then I'll do a little recap of these basic properties of log. Recap of basic properties of log. So we know that e to the a plus b is just e to the a, e to the b, right? Because this is e multiplied by itself, a plus b times, right? Which is the same as multiplying e to itself, a times multiplying e to itself, b times, right? This is a straightforward algebraic fact. And log is the inverse, right? Log is the inverse. So what we have to have is that a plus b, which is log of e to the a plus b, it's got to be the same as log of e to the a times e to the b. Yeah? So, for any x, y, which are positive, because log is only working on positive numbers, let a equal log of x and b be log of y. So in particular, we have that e to the a equals x, e to the b is equal to y. So if we put this into what we've just learned, then let's call this thing star. So star says that log of x plus log of y equals this thing, which is equal to log of x times y. And that's the property of logs, okay? The other ones follow from this. You can work that in the same way. So this is the basic property of logs that we used in the previous example. Cool, so previous example, well, actually we have one more thing we want to do before we get into log differentiation. Final clarifying example or useful example of log, of calculating derivative of log is the following. Log is only defined for positive numbers, but it's often convenient to have something which we can plug into log, which isn't just positive. So we end up thinking about the following function, log of absolute value of x. So this is an example. Differentiate log of absolute value of x. Okay, solution. First, let's get some idea what we think it looks like, and then let's do the calculation and see if we conform with the picture. So what do we think it looks like? So log for positive x looks like this, right? And this is 1. And this function, log of absolute value of x, doesn't notice if we are on negative or positive x, right? Because we put the absolute value in. So whatever we have here, whatever value we have, if this is x, then over here, the minus x, we have to have the same value, right? Log of minus this thing has to be the same as log of this thing. So we're going to have a mirror image of whatever we have here reflected onto the other side of the y-axis. So we're going to have a function that kind of looks like this. Yeah? This is what the function looks like. Cool. All right. So let's actually differentiate it. So if we think about what log of absolute value of x is, it's defined for positive x as the following. It's just defined of log x if x is bigger than 0, and it is log of minus x if x is less than 0. Yeah? Cool. So if we differentiate it, let's break the two cases up. If we take the derivative of log absolute value of x, then positive x, this will just be 1 over x, because it's the case that we know. But for negative x, then we're going to have to apply the chain rule, because the inner function is minus x. So we're going to have 1, oops, properly. We're going to have 1 over minus x, and then we differentiate the inner function, which is minus 1. So then this is just, again, 1 over x, if x is less than 0. Now let's check with the picture. So we're happy with the right-hand side with x positive. Yeah? On the left-hand side, the slope is negative, and it's more and more negative as we get towards 0. Yeah? But that's what we see, because 1 over x is negative if x is negative. Yeah? So this thing conforms with our picture. Another thing to notice is that the derivative on the right-hand side is minus the derivative on the left-hand side, which is again what we see. Right? So we believe this, and we have this general fact is true. So d by dx of log of absolute value of x is just 1 over x. I need to write this better. For any x non-zero. All right, excellent. Now, log differentiation. Let's consider the following example. If we wanted to differentiate this really complicated looking expression, all right, so we can do it, right? Because we can do each part of this. Is the quotient, we have some chain rule, power rule going on. We could do this, but it's going to be a long calculation. And if I was doing this, I'd have to do it at least 3 times to be convinced that I got the right answer, right? So if we can, we'd rather avoid working too hard. And this is what we're going to do. So step 1. Take logs of both sides. And if we do, then what happens? We have log of y of x, and then log of this thing. But log of this thing, we can apply our log rules and make it much simpler. So first of all, let's break it up into this log of the top minus log of the bottom. Let's pull out the 5 straight away. Okay, and further breaking it up, we have this is 3 over 4 log of x plus 1 over 2 log of x squared plus 1, and then minus 5 log of 3x plus 2. And now what? Now we differentiate both sides. If we differentiate both sides, we've learned that the derivative of log of y is y prime over y. So then we're going to have d by dy, d by dx of log of y of x is y prime of x over y of x, and then all of this stuff, which individually, each one of these things is easy to differentiate because we're differentiating the sum of a bunch of easy functions. Yeah? Okay. But now we see how we can find y prime. We just have to multiply everything by y of x. I'll multiply the left and the right hand side by y of x, and we have that y prime of x is equal to and then this stuff. Yeah. And that is our answer. And that is a lot easier than dealing with this thing just by quotient rule, product rule, power rule, chain rule. Yeah. And this will, I mean, you can imagine if we create any other kind of very complicated expression involving products and quotients and powers, this thing will go easily with this method. And without it, it's just going to be a really long, difficult calculation. So this is a powerful tool. This is a hammer. We have a very nasty expression. We think of the hammer, bring out the hammer, and we can just flatten it rather easily. Yeah? This is also a very common thing to ask on the free response, because any student can make some sort of progress on this. Well, hopefully any student, they will remember something, will be able to start at least this thing. Yeah? And if they're very diligent, even if they don't remember log differentiation, they can get to the answer. Perhaps even the right answer, which would give them 4 points, but it will take a long time. But if you are a diligent student and you remember what we're teaching you today, then you say, okay, I'm not going to do this the hard way. I'm going to apply log differentiation, and you get the answer quite quickly, quite easily, with little chance of mistake. Okay, so if you want to strategize, and I think you should, the best way to do well in these exams is think about what kind of questions we would most likely reasonably ask you on the free response, and what would most likely ask you on the multiple choice. And we tend to ask more or less one question per topic, right? Because we have a lot of topics we cover in between midterms. And this would be a natural thing for the free response. I can't guarantee it, but it certainly happened before, and it's a natural one. Okay, let's do some more examples of this stuff. Let's use it to find out the power rule. So we had this kind of algebraic proof of the power rule that we discussed before. Log differentiation gives us a really slick one. So if we want to differentiate, we know it's n x to the n minus 1. If we do the following, so let f of x be x to the n. Yeah? Then let's take log of f of x. That is just going to be n log of x. Right? And then differentiating, we're going to have that f prime over f is just going to be n over x. And then put the f on the other side, we have that f prime of x is equal to, since x to the n, but we have what's 1 over x, n x to the n minus 1. Really fast, really slick proof of the power rule without this complicated algebraic cancellation that we saw before. Not that it was super complicated, but it was a long expression we had to analyze. Yeah? Cool. Let's do another example. Y of x equals x to the square root of x. Okay, so this would stop many students. So I've seen many exams where students panic when they see this and they try and apply the power rule. This is not the power rule, right? This is not a function you apply the power rule to. This is not x to some fixed number, n or whatever. This is x to the square root of x. So this is to be your mindset. You see something difficult to differentiate, don't panic, think of the hammer, log differentiation. So log differentiation, we apply logs to both sides. So you log, and then this will just become square root of x, log of x. Differentiate both sides. So we're going to have y prime, y of x, and this thing we can differentiate, it's just the product rule. All right, so we have 1 over 2, x to the minus 1 over 2, log of x, plus square root of x over x. Yeah? And what's this? This is equal to log of x over 2 square root of x, and this guy here is just 1 over square root of x. Now this entire expression is just log of x plus 2 over 2 square root of x. And that's it. Well, that's it for the derivative of y prime over y. It's not quite it because we have to actually get y itself. So prime of x is equal to times all this stuff. And in this particular case, I don't think you have any chance to get the answer except from doing log differentiation. Okay. Certainly there's no rule that we've taught you that's going to help you here. Maybe if you work with the initial definition, you work really hard, you'll get something, but it's not looking like it's going to be an easy thing. So that is one of our classic examples. And there's lots of these things we can cook up when it's some kind of thing, function to the power of another function, apply log differentiation, and you're going to be fine. Okay, so we have a final application of these kind of ideas. I don't want to squeeze it in, so I'm going to raise the board and talk about it when the board is clean. Okay, the final application is we're going to find out the value of E. So I've told you it's 2.71 something something something. I haven't told you why it is this. Let's find out why it has this value, how we know it's its value, how we can actually calculate it. So we start with the following limit. Let's think about this limit. The limit as x goes to 0 of 1 plus x over 1 over x. So this is not an obvious thing at all, right? Because as x gets closer and closer to 0, actually from the right-hand side I should specify, then this guy is getting closer and closer to 1, but this guy is getting closer and closer to infinity. So it's a kind of a battle about what happens faster, because if we have a number and it's bigger than 1 and we keep taking higher and higher powers of it, it blows up, right? But as x goes to 0, this gets closer and closer to 1. And if we have a number which is really, really close to 1 and we take a very high power of it, then it isn't much bigger than 1, right? So it's what happens first. So this limit is really unclear, right? It's really not clear to us what's going to happen, who's going to win this battle, or what the result of this will be, even if the limit exists. So what we're going to do is we're going to take log of both sides. Okay, so if we take log, well, let me say not both sides here. Let's take log of this entire expression. So let's let f of x equal this an expression like this, and then let's take log of it we're going to have log of 1 plus x over x itself, using these properties of log, right? And if we look at that, then what's that? That's the same as log of 1 plus x minus log of 1, because log of 1 is 0, over x. You know? And what's this? Well, this is just the derivative of log if we let x tend to 0 and take the limit. Yeah, it's the derivative of log at actually 1. Yeah? So d by dx of log of x I don't know how to write this. D by dx of log of x is equal to limit as, because we used x already once. All right. Okay, let me just write this. This thing is log of x plus h minus log of x over h, right? That's the definition of derivative. So this thing, well, this thing star, so forget about that. I'll write this. So the limit as x tends to 0 of log (1 plus x minus log of 1 over x) is just the derivative of log applied to 1. And the derivative of log is 1 over x. Applied to 1 is just 1 over 1, which is just 1. Okay? So this thing is just this thing. So the limit as x goes to 0. So I took x to 0 from positive numbers because I didn't want to think about negative powers, because it's just going to overcomplicate things, but it doesn't matter because this limit exists. So this is just to make it an easier thing to understand, but it's not an important thing. We've actually seen that the limit will exist as x tends to 0 no matter what, right? So the limit as x tends to 0 of log of f of x is this thing, which is this thing, which is this thing, is just equal to 1. Yeah? Cool. All right, but that isn't the actual thing that we're looking at. We're meant to be trying to understand this, right? So this implies that limit as x tends to 0 of log of 1 plus x over 1 over x is equal to 1. But e is a continuous function, right? E is a continuous function. So if we do the limit as x tends to 0 of 1 plus x 1 over x, that's the same as the limit as x tends to 0 of e of log of 1 plus x the 1 over x, just because e and log are the inverses, right? And as we talked about before, if we have the composition of continuous functions, right, and we are passing to the limit, then we can take the limit through the first function, right, which just came back from pictures. So go back if you feel unclear about this. We draw two pictures, we trace what would happen as we get closer and closer to the limit we're going to, passing through the first function and then the second function. It was just these two graphs. So this allows us to take the limit through this e, which is continuous, and it's the same as the limit as goes to 0 of this guy now, and we found out that this thing is just equal to 1, which is just e of 1, which is just e, which is this mysterious number that we want to find. So we found out that this thing in the limit is e. So in particular, if we want to approximate e, we can just plug in small values of x. So the limit as n goes to infinity, where n is a natural number, of 1 over n to the n is equal to e. So if we want to get a good approximation for e, then we can just plug into your computer, your calculator, some large value of n. So i.e. for n equals whatever 1,000, then 1 plus 1 over 1,000 to the power of 1,000 is some number which is pretty close to e, 2.71 blah 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 blah. And the better approximation you want, the higher power of n you'll stick into this, and that is how you'll calculate e. That's actually how we know this value of e. So that's another thing that we can find out. And what we use this idea of log differentiation, but in this case we used it to simplify this 1 plus x to the 1 over x. So I said in the last word that whenever we have something to some power and the power is some kind of function, we don't want to deal with it. We want to apply log and then bring down that power, because then we can differentiate it. Well, it also is the case that then we can take the limit of it, which is what we want to do here, and find out this answer and actually have an exact answer for what e is. Okay, so this is a useful thing to be able to do, right? So if the world ended, if there was a if there was a total destruction of the world, and we're back to the Stone Age, and we have to rebuild science, rebuild everything, then one of the things we're going to need to know is logarithms and exponential functions, and we have to make calculations with these things without computers, and we need to know the value of e. So hopefully some of the survivors will remember this argument and be able to recapture e, and then civilization can rebuild. All right, so that's enough for today. Have a great weekend. I'll see you all next week.